Welcome back to another video. In this tutorial, we are going to dive into the concept of differential geometry. Differential geometry. Okay, so basically, if we talk about differential geometry, it is the study of surfaces, curves, and higher dimensional spaces using calculus and linear algebra. Okay, so it focuses on concepts like manifolds, right? Manifolds. Concepts like manifolds. You know what manifolds are? Manifolds, they are basically, they look, they are in space, right? And they look flat locally, okay? But they can be curved globally, right? So look at an example, breast illustration for manifolds, right? So you know coil, mosquito coil, how it looks like. That is same way manifolds looks like. Okay, so that is, so you know coil, the way coil is, yeah, that's how manifolds are. So you can think of going this way, going this way, going. That is how manifolds are. So look at how coil is. It moves like, you see the way it's, okay, so that is how manifolds are. It's one of the concepts in differential geometry. And two, it also looks at tangent spaces. Okay, tangent spaces, they basically define direction on curves. They define direction on curves. And also, we can look at curvature. Okay, curvature. You know, curvature basically measures uh, how much a shape bends. So when we talk about curvature, simply think of how much a shape can bend. How much a shape can bend. Okay. And look at this one, the other one, a radius of curvature. Okay. When we talk about the radius of curvature, look at this illustration. Okay. This is a circle inscribed in, I don't know how you call this, but this is a circle inscribed in something like circle. It looks like a circle, but not a circle. But okay, so we have a radius here. Okay, so let's name this C and name this E and name this place A and B. So this here is our radius of curvature. This here is our radius of curvature. So basically the radius of curvature is shown over here. Okay. The next concept that differential geometry looks at is unit tangent. You know, unit tangent, when it comes to unit vectors, it's basically a vector that has a magnitude equal to 1. You know that, right? Unit vectors. It's a vector, that has a magnitude equal to 1. So if we talk about unit tangent, it's basically a vector that has a magnitude equal to 1, and it's in the direction of the velocity vector. So let's look at best illustration. So the illustration for unit tangent, let's say you have a plane here is x, and you have another axis here. You know, if this is the radius, okay, this is the radius, let's make it short, okay, and there is a wave, something like a wave that moves on this radius, right? What you have here, okay, what you have here is your unit tangent. This is your unit tangent. This is your unit tangent, okay? What we have here is our unit tangent. So that is the best example I can have for you for the unit tangent. Okay, you know it is a vector that has a magnitude equal to 1 and it's in the direction of the velocity vector. So that is what we have here. You know, velocity is basically a vector quantity, right? So that is what we have here. That is what we have. So that is a concept in differential geometry. So these are concepts in differential geometry and some other ones like principal normal and you can principal normal. When you talk about the principal normal, that is where you see the okay, when you talk about the curvature, that is when you see the principal normal in there. You know, those who read physics, okay, physics, you do what we call the center of curvature, and that is drawn this way. Center of curvature, you have something like this, and you say this is your mirror. This is your mirror having a reflection, okay, behind, and this is your, you name this part and you call it principal focal length. Principal focal length. And the mirror, the image that appears here, you said you call it the image that appears there, you call it center of principal normal. How that is interesting. So you know the differential geometry, it's basically a field that really helps. It really helps, okay? And the key ideas includes geodesics. You know, geodesics, they are the fastest, do I say the fastest? Geodesics, they are the shortest part, on surfaces. They are the shortest part on surfaces. And we have what we call the parallel transport. This power transport defines how vectors move on curves. The power transport defines how vectors move on curves. Okay, so basically that is the concept that is in geometry or differential geometry. So when it comes to differential geometry, it's very important in these fields, okay? When it comes to physics, general relativity, and when you go to engineering fields, we use it in graphics and robotics as well. And when it comes to mathematics, the field of the center of everything, we use it in topology and we use it in differential equations. So differential geometry is very key. All right, so that is what it focuses, or that is the concept it focuses on. Now we are going to dive into four key aspects, and that is the unit tangent, 2, the curvature, and 3, the principal, no, the third one is the radius of curvature, and the fourth one is the principal normal. Okay, so this basically are the formulas for the unit tangent, the curvature, and others. Okay, so for the unit tangent, for the unit tangent, denoted as capital T, is equal to, you know, if you want to find the unit tangent, okay, when it goes to unit vectors, if you want to find a unit vector for a particular position, something like whatever vector, it's the position vector of that particular particle, okay, or the position vector of that particular argument over the magnitude of the position vector, right? In here, the unit tangent is the differential of the radius over the magnitude of the differential radius. And you know that radius, the differential of radius gives velocity. So you can also define it in another way, that unit tangent can be obtained as velocity over the magnitude of velocity. So we have here differential of the radius over the magnitude of the radius of the differential radius, and that is equal to velocity over the magnitude of velocity. That is interesting, right? B, talk about the curvature. Okay, so the curvature denoted as capital T is obtained as, the curvature is basically um, the unit tangent. When you differentiate the unit tangent, right, you have your curvature, the differential of the unit tangent over the magnitude of the differential radius. So the differential of the unit tangent over the magnitude of the differential radius, and the result obtained, you take absolute or magnitude of the result. So differential of the unit tangent over the magnitude of the differential radius. Then the result, you take magnitude of the result. That's interesting, right? So let's look at the third one, which is the radius of curvature. The radius of curvature is the reciprocal of the curvature. So if you know the curvature, then automatically you are good to go with the radius of curvature. So radius of curvature denoted as capital R is equal to the reciprocal of the curvature. That is how you obtain the radius of curvature. The last one, which is the principal normal, is obtained as principal normal denoted as small n, is obtained as, the principal normal. You see, looking at the illustration, if you want to obtain the principal normal, then you're going to talk about the unit tangent, because it's basically the differential of the unit tangent over the magnitude of the differential unit tangent. So that is differential of the unit tangent over the magnitude of the differential unit tangent. Wow, talked about. Let's go. So with this problem, it says a space curve is given by this parametric equation, right? We've talked about parametric equations, and you know what parametric equations are. Okay, so we have x equals 3 cos t and y equals 3 sin t, and also z equals 4t. So we have to transform this parametric equation into a vector, position vector, right? So let's say that r equals 3 cos ti plus 3 sin tj plus 4tk. Okay, so we have our radius. This is all we need. Then the rest is just differentiation and finding magnitude and all that. so interesting in differential geometry. Is so interesting. Once you get one solution, it runs through, it helps you to get the rest. So let's go. So let's find the differential of the radius, okay? Because we know that unit tangent is differential of the radius over the magnitude of the differential radius. So let's find the radius of the differential of the radius. So differential of the radius will be equal to differential of 3 cos t, differential of 3 cos ti will be negative 3 sine ti. You know, differential, of course, is negative sign, right? Plus differential of 3 sine tj becomes plus 3 cos tj. Then differential of 4tk, you know, we are differentiating with respect to t. So differential of 4tk becomes 4k. 4k. So this is the differential of the radius. Once we have that, the next thing we have to look for is the magnitude of the differential radius. Then we can obtain the unit tangent. So the magnitude of the differential radius will be equal to 3 square root of 3 sine ti all squared plus 3 cos tj all squared plus 4k all squared. Right? So we're going to have square root of 3 sine t, that is negative, right? So negative 3 sine t I squared becomes 9 sine squared t plus, you know, magnitude of a unit vector, magnitude of I is equal to 1, right? So you know, you even don't have to bother about that, right? Then 3 cos t squared becomes 9 cos squared t plus 4 squared becomes 16, right? So we have this here. So we're going to have 9 sine squared t plus 9 cos squared t. We can factor 9 out to have 9 into sine squared t plus cos squared t, bracket close, plus 16, right? And we know that sine squared t plus cos squared t is an identity in trigonometry, right? And that is equal to 1. So we know that, but sine squared t plus cos squared t is equal to 1, right? So once we know that is 1, we substitute in place of that, okay, so that we can simplify the square root. So we're going to have our magnitude of the differential radius will be equal to square root of 9 into 1 plus 16, right? So we have that to be equal to square root of 9 plus 16, and that is square root of 25. So basically we have the radius differential of the magnitude of the differential radius to be 5. Wow. So we have the magnitude of the differential radius and we have the differential of the radius. So now we can find the unit tangent. So we know that unit tangent, that is the big T, is equal to differential of the radius over the magnitude of the differential radius. So that will be equal to negative 3 sine t I plus 3 cos tj plus 4k, right? All over 5, right? So basically, we are going to have big T to be equal to negative 3 over 5 sine Ti plus 3/5 cos Tj plus 4/5k. So this becomes our unit tangent. So thus our unit tangent is obtained over here. Okay, once we have the unit tangent, then we can proceed to find our curvature. Okay, so let's find our curvature. So we know that curvature, curvature, B, curvature, curvature, which is the big K, is equal to the differential of the unit tangent, the differential of the unit tangent over the differential of the radius, the differential of the magnitude of the differential radius. So over the magnitude of the differential radius, then this one, everything is now, when you are done taking this, then you take the magnitude of the result. Okay, so that is how the curvature is being obtained. So that is big absolute sign, right? So now we have our unit tangents and we have our differential of the radius. So we can go ahead and do the necessary. Okay, so over here, what we just need is to find the differential of the unit tangent. Then we know the magnitude of the differential radius over here as 5. So the only thing we need is the differential of the unit tangent. Then we can take the magnitude of the result. That's it. So here, the differential of the unit tangent, the differential of the unit tangent will be equal to differential of negative 3/5 sine t. You know, when you differentiate sine, you have cos, right? So we are going to have negative 3/5 cos Ti plus, when you differentiate cos, we're going to have negative. So we have minus 3/5 sine Tj plus, when you differentiate 4/5, you have 0. So that part goes off. So that is it. So we have the differential of the unit tangent. What we need next is to find the magnitude of this over this, right? So we're going to have the differential of the unit tangent over the magnitude of the differential radius to be equal to negative 3/5 cos Ti minus negative 3/5 sine Tj all over 5. So that is what we have here. So you know that for sure, when you take this, you're going to have magnitude of the unit tangent. So now let's take the absolute, okay, of the result we are having. Okay, so when we take the absolute or the magnitude of that, then we are going to have our curvature K to be equal to square root of negative 3/25 cos Ti all squared plus negative 3/25 sine Tj all squared, right? So we're going to have square root of 9/625 cos squared T plus 9/625 sine squared T, right? So basically, this are what we call perfect squares, right? Perfect numbers. So basically, we can factor this 9/625 out. So when we do that, we're going to have 625 inside the square root sign, okay? Then we have cos squared t plus sine squared t inside again. So we know that this is a property, absolutely, it's equal to 1. So we're going to have square root of 9 over 625 into 1. Right. This is so interesting. This is so interesting. So we're going to have square root of 9 over 625, right? And that is basically 3 over 25. Wow. Wow. That is interesting. So we have the curvature. What is next? Our radius of curvature, okay, which is denoted as big R, will be equal to 1 over 3 over 25, right? And that will be equal to 3 over 25 over 3. That is great. So that is the answer for radius of curvature. We know that the last one, which is D, we know that principal normal denoted as small n is equal to the differential of the unit tangent over the magnitude of the differential unit tangent over the magnitude of the differential unit tangent. Right? So that is basically going to be, we have our unit tangent here as negative 3 over 5 cos ti minus negative 3 over 5 sin tj, right? Now we have to take the magnitude of that. Okay, so let's try to take the magnitude of that over here. So the magnitude of that is going to be, the magnitude of the differential unit tangent will be 3 over 5, that is negative 3 over 5 cos ti squared plus negative 3 over 5 sin tj squared, right? So you're going to have that to be 9 over 25 cos squared t plus 9 over 25 sine squared t, right? So basically, we are heading towards the end line, and this will give us 9 over 25 into cos squared t plus sine squared t, right? So that is equal to, this is absolute equal to 1, right? So we have 9 over 25 into 1, okay? And that is square root of 9 over 25. So we have 3 over 5. Wow. Wow. That is so brilliant. That's so brilliant. So we have 3 over 5 as the magnitude of the differential unit tangent. So what do? We take this, divide by the differential unit tangent. So that is going to be this, right? And that will be equal to all this over 3 over 5, right? That is so simple. So basically, this, when you reciprocate it, you know that this is 3 over 5, and you have 3 over 5 running through this. So you're going to have negative 3, negative cos ti, minus 3 minus sine tj. So basically, we are down the line. That's it. We are down the line. So that is it. So our principal normal denoted as small n is equal to negative cos ti negative sine tj. Wow. Wow, that is interesting. I really love that. So that is the process and that is the concept behind differential geometry. I love that. Thank you very much for watching. I really appreciate your time. Don't forget to subscribe, share with your mates, and I'm going to give you more updates. Bye-bye.